in this lesson, we are going to talk about two of our four types of variation. You might remember that in class, what was it, probably Tuesday or Wednesday of this week, we talked about how there's four types of variation. You'll learn two in Algebra 1, you'll learn two in Algebra 2, okay? Obviously, direct variation is one of those four types, because that's what we've got here at the top of the screen. What's another of those four types? Did you write all four of them down, the names of them? We got direct. What's another kind, Connor? Inverse. Very good. Those are the two that I'm going to teach you this year. And then there's also what's called joint variation, okay, which is where there's multiple factors, all of which directly impact the output. And then there's what's called combined. Okay, so you got direct, inverse, joint, and combined. Combined is where you have a little bit of direct and a little bit of inverse. Okay. A couple things that we made mention of in class on Wednesday, we said that direct variation is a linear relationship. You've got to make sure you understand that. A linear relationship, okay? And then what we're going to look at is we're going to put into use three steps, okay? There's a lot on the screen, I know, but what we're going to focus on with this example about Raul on the treadmill at the gym burning some calories is I'm going to take you through steps 1, 2, and 3. Okay, simple as that. Steps 1, 2, and 3. Stephen. Yeah, it's actually going to be for direct and inverse. So it'll be the three steps that we use in our two examples today. Okay. Now I'll leave these up at the screen, but I'm going to slide down so we got a little bit of room to work. Raul is running on the treadmill. The more he runs, the more he burns. That's common sense. Okay. So when I have an input that goes up, and as a result, my output goes up. That's direct variation, okay? An increase of time spent running is going to increase the number of calories burned. So what we're going to do, step 1, is going to write the equation. So it says the calories burned varies directly as the number of minutes running. So I'm going to say C equals K times M, where K is my constant, Dominic, of variation or proportionality, whatever you want to call it. Step 1, set up the equation based on the given info. Done. Second. Be more specific. What part doesn't make sense? You feel like what? Well, let it play out and see if you're still confused. I bet you won't be. I bet you won't be. C equals Km. Okay? All right, step 2, I want to highlight a phrase called initial condition, okay? The initial condition is where you're going to be given a data point, okay? Pretend like, back here a moment ago we were talking about how this is a linear relationship. This is as though I'm telling you, hey, there's this line that's going from the origin out up into the right, and oh, by the way, here's this initial condition point. I'm going to tell you when X is this, Y is that. And I'm going to let you use, Dominic, take your hooded jacket back off, please. I'm going to let you use X and Y to find the slope of that line, because that's really what K is. K is our slope. So, all right, so step 2 says use the initial condition. What does that mean? They say when you run for 18 minutes, you burn 315 calories, or at least Raul does. All right, so 315 is going to go in place of C. 18 is going to go in place of M. All right. Now, what that is going to allow us to do with step 2 again is to solve for K. I want you to divide both sides by 18. Divide by 18, and you wind up, look here in blue, you get K equals, what's 315 divided by 18? Anybody run that number yet?
100 something.
All right, 100 something ain't getting the job done. Yeah, we could use a calculator. That's not a problem. 315 divided by 18. 17.5. You had it doubled. 17.5. Now, in the context of this problem, what that means is that that's the number of calories per minute that Raul is burning. That's all that is. That's a constant. So Raul is a young man, so at a constant weight with his metabolism on this particular given day, he's burning 17.5 calories per minute. Now what we can do then, step 3, is we can use that rate use that. That's the slope of the line, by the way, right? If you consider it to be a line, bless you, that's the slope of that line. Okay. Now, Raul, he's got his orange line. Somebody with a higher metabolism might burn calories faster. Some old guy like me with a lower metabolism might burn calories slower. Okay. So all three of those lines would have all different slopes. Okay. The slope in our little example right here is the rate at which he burns calories per minute. And then look at step 3. Step 3 is where we're going to take that value that we just solved for K, plug it in with the other missing, or with the other parameter, and find the missing value. So it says, how many calories would he burn if he were to run 25 minutes? So all we have to do is times it by 25. We get 437.5. All right, and that's the number of calories that he would have burned in 25 minutes. Okay, Stephen.
I thought that we have to assume he's just eating the same pace.
Say that again.
Like, are we just assuming he's like going at the same speed?
Real good point there. Real good point. And in just a sec, we're going to talk about a guitar string and like frequency and length of the string. And the assumption is going to be there that it's at a constant thickness, right? It's that it's one guitar at a constant thickness, at a constant tension, all that jazz. So real good point to be made here. Now, visually, again, speaking visually, what we just did, check this out up here, guys. Whoops. We were given an initial condition, weren't we? We were told that at 18 minutes, he burns 315 calories, okay? And then we came back and we said, all right, well, how many calories would he burn if he ran for 25 minutes? So we took the information that we were given, and then that third step, we extrapolated some additional information, okay? Like how many calories he would burn going 25 minutes. And you could do this on and on and on and on and on. Sebastian.
Wait, K is how many calories per minute?
In this case, yeah. K, when we solved for K, and by the way, it might be a good time to mention what I've got right here on this slide. When we solve for K in a direct variation problem, K is sometimes referred to as the constant of proportionality, because the way that you would solve for K is you would divide the output over the input, Y over X. Okay, isn't that what we did? We said down here at the bottom, we said, oh, let me divide both sides by M to get K by itself. Divide by M, divide by M. So what was it? Calories per minute. 315 over 18 was calories per minute. So the reason they call it the constant of proportionality is because right here is a proportion. You could do output over input, output over input, output over input. And some guys like Will Perone in first period sits back there where Cam's sitting. He said, hey, that's how I've solved them before. Can I do that? I said, yeah, good on you. All right. So knowing how direct variation works, we can then answer further questions. Like I'm going to give you a further question right now. You guys will chew on this. Okay. How much would Raul have to run? Let me continue my little orange line right here. How much would Raul have to run? Maybe he's a wrestler and he needs to burn a certain number of calories. Maybe I want Raul to burn 570 calories. You know, how long would he have to run to do that? Because we've been given this initial condition, in other words, we know K equals 17.5, how are you going to do that? Yeah, set the formula up as 570 goes in place for C. I know this boy's fixed rate of calories per minute is 17.5, and so the only thing to solve for is M. So we're going to divide 570 by 17.5. What'd you get, Eli? Or did you divide? Divided by 17.5. How many minutes? About 32.6 minutes. Just rounding. 32.6 is how many minutes he'd have to do. We get that just by dividing. And again, this process is called extrapolation, where you take a data set and you use it along with the model that fits that data. Do y'all do that in your science class ever with Mr. Niggle? Y'all collect data and then find like a line of best fit? Or,
Trend line?
pardon?
The trend line?
Yeah. He calls it a, would you say a trim line? Trend line, pardon me. Yeah. And so then you use that trend line to predict future behavior. That's called extrapolation. What's interpolation, by the way? If extrapolation is where I use a data set to predict behavior outside, yeah, I use the data set to help fill in its own gaps. In other words, interpolation is like where it's inside the data set. Something's missing, in other words. So extrapolation, you pull it for the outside. Interpolation, you pull it for the inside. A couple neat little vocab words. All right, so that's direct variation. Let's talk about inverse variation before we get into y'all's homework questions, because I know you got some. Okay? Inverse variation is you're taking good notes. Hopefully all of you are. As you're taking good notes on this, inverse variation is not a linear relationship. It's actually a hyperbolic relationship. The graph would look like this. Inverse variation is where the more I put in, the less I get out. The more I put in, the less I get out. Okay? This is like driving at a fixed distance. Let's say I got 100 miles to go. The faster I drive, the less time it takes. And the slower I drive, the more time it takes. That's an inverse relationship. I also used the example in class earlier in the week about a balloon, right? At a constant temperature, a decrease in volume is going to increase what? If I squeeze a balloon down to where it's half the size of what it was, what's increasing? The pressure. That's common sense, right? At a fixed temp, I don't know, what is that, Boyle's law? What do they call that in physics or in chemistry? Anywho, there's an inverse relationship between pressure and volume, and again, that's what we're studying here. All right, same three-step process. So y'all walk through this with me here. Down in the guitar string, it says the frequency varies inversely with the length. So I'm going to say F equals K divided by L. Zach, I did. It's cranked up, baby. It's just cold today. Y'all deal with it. I know Dom's back there rubbing his arms. Dominic, if you roll those sleeves down, it'd be a little easier for you.
Okay. They go to like right.
Put them in your shirt. Like
Oh, I hate that. I hate that. Do it.
I remember how you used to like just crumple up and just fall asleep.
I got my window open. I got the door open. We got a good whoosh of air coming right in through here, and I got the heat cranked up.
And why don't you close the window?
I'm gonna close your daggum window, Sebastian.
I'll close it.
Why don't you close your window? I'm keeping that window open to keep some nice fresh air flowing right through here. Get all y'all's cooties out of the way.
Well, we're boys.
All right, y'all shut up and get with the program. Here, write the following down. Seriously, write the following down. Because sometimes I get students that they'll get confused between what's what on variation. If it's direct variation, you're multiplying. If it's inverse variation, you're dividing. That's a real simple way of looking at it. If it's direct multiplication, it's multiplying by your constant. If it's inverse variation, then it's going to be dividing. So in other words, if it says the frequency varies inversely as the length, okay, so frequency equals K divided by the length. All right. And then step two, so that's step one. Step two, they're going to give me an initial condition. They're going to tell me, all right, it's got a frequency of 440 when that string is 26 inches long. So I just plug and chug. All right, Cole, what do I do to get K by itself now?
You multiply 26.
Yeah, multiply both sides by 26. I want to say it's 11440. Let me double check. Nobody cares, Zach. Be quiet. Times 26. 11440. Attaboy. Thank you. I'm gonna say it's blah blah blah. Look at you back there. Times both sides. Listen to Cole Carlson. He told us times both sides by 26. Right, to get K by itself. All right, now in this case, I've got K, so my third and final bit is to say, all right, well, how many vibrations will there be? So F is unknown. Now I know what K is, 11440, and it says here we got a length. Now a string is 20 because I'm putting my finger on the fret and holding it down to a shorter. By the way, do y'all know, like, do y'all play stringed instruments? Anybody in here play a string instrument?
For a really, really long time.
A couple of you guys do? Giving in the problem. Giving in the problem. So, like, if you play, Dominic, do you play guitar? No? If you, Peter, so, like, you guys know that, like, the higher up on the neck that you go when you're shredding that guitar solo, the string is getting shorter, and therefore the tone is getting, or the pitch is getting higher, right? So like when you're going up the neck of the guitar, you're shortening up the length. You are increasing the frequency. A high-pitched sound has a high frequency, okay? So the longer that string gets, that's why a bass guitar, somebody in my first period class plays bass guitar, right? Justin Bowers was telling me he's learning to play a little bit of the bass. And, a bass guitar's got a big old long neck on it, doesn't it? That's a long string so that it will have a lower frequency, okay?
Bass is not really making noise, that much noise that,
True that, unless you got yourself a good old, what do you call it, a double bass, like what you might see rocking out at a concert. All right, by the way, I don't know what number this was. Let me divide by 20, 572.
572.
Thank you, Zach. Spot on as usual. All right, but look, fellas, here's the rundown, okay? Follow the 3 steps and you'll be fine. Joint variation, when you guys get into Algebra 2, is just as easy, okay?
This isn't as hard as the dirt problem.
I totally agree, 100% agree, right? Speaking of which, let's get to the homework. Go for it, Sebastian.
They can't get any harder than that.
Speak up louder.
The question can't get any harder than that.
No, I mean, like, even what I was going to say a moment ago, even when you get into Algebra 2 and you do with joint variation, all that's like doing is saying, okay, the number of calories burned by Raul varies directly as the time he spends running and the speed he spends running and the incline that he spends running. Okay, so that would be where you would just say, like, okay, C equals K times this, times that, times this. So like combined variation will be, okay, maybe you multiply by a couple things and maybe you divide by a couple things. So they just introduce a few more parameters. Really, the step-by-step process doesn't change it, okay? Now, y'all have some questions, I'm assuming, on the homework. Get your homework out if you don't have it out already. And what were some of the things, yesterday, we were going to do this lesson yesterday. While I was on senior retreat, you were going to watch a screencast going through those last 2 examples on variation, and then you were going to sit about working, right? You were going to work. And then we're going to come in today and do Q&A. Well, you didn't have a work day in class yesterday, so I want you to work a little bit for me in class today, but at the same time, we'll do some Q&A, all right? So somebody had a question on one of them. All right, Eli, so you got a hand up. What's your question?
On 295, what about the car and jet? I just flipped it.
All right, you know what? Let me get this out of the way. We had a great discussion on this one earlier today. And let me do this. We'll get this out of the way. If OneNote will wake up for me, please, and thank you, OneNote. All right, sweet. So first of all, I think the hardest part of these problems, fellas, to be perfectly honest with you guys, is getting them set up. Getting the equation set up. If you can get the equation set up, you got a pretty fair chance of figuring it out, okay? So as I read this problem, I'm going to say Hudson travels 1,080 miles, stop right there. You saw me write it a minute ago. I'm going to put dirt, distance equals rate times time, smack dab at the top of the paper because I know that's the type of problem that this is. Dominic has identified, it's like, man, these are some of the hard ones, okay? Good. I'm going to write everything down that I can on the hard ones. The easy ones I might be able to do in my head. The hard one, I'm going to write everything down, all right? Hudson's traveling by jet for a little ways, and he's traveling by car for a little ways. So there probably will be one row. Remember, you can use a chart. There will be one row for the jet and one row for the car. Okay, so let's think of it that way. We got the jet, and we got the car. And we got rate, time, and distance. Okay, you don't have to use a chart, but again, if you're struggling, they're going to use one. All right, now it says about the jet, it's 300 faster than the rate of the car. The question asks what's the rate of the car, so why the heck wouldn't I just say, let X be the rate of the car. Let X be the rate of the car. So how would I express Maxwell Posey? How would I express the rate of the jet, the speed of the jet? If the car's going X and the jet's 300 faster than that, X plus 300. You see how the puzzle's starting to take shape, guys? Now about the time, I don't know about the time, but I do understand that the jet's going faster, so his time will be smaller. And I kind of like letting the smaller value be my variable. So why don't we let t be the variable for the amount of time that the jet goes. And then did you read it where it says it takes the car an hour longer? So yeah, very good. T plus 1. Okay. That's cake so far. We're just plugging and chugging, baby. And then distance, how do I get distance? Well, they gave it to me. Duh. 1080 and what? 240. Always helps to read the problem, right? So now I've got my sort of puzzle pieces laid out on the floor, laid out on the table, what have you. OneNote is having a little trouble here. Hold your horses. If I do too much too quick, OneNote wants to stop. There we go. Now, there are two variables that we ended up using. So I need to be able to do what? Somebody said it. I got to be able to write two equations. Dominic, pay attention, baby. Okay? Quit distracting. And also, you need to get a haircut. I'm tired of telling you. Got it? You going to get one over the 3-day weekend?
I'm getting one.
That boy. Zachary? Yes? How about maybe I email Dean Bunkley and your parents and say, please make sure Zach gets a haircut. I'm trying to let you handle your business on your own. Get you a haircut. Snip, snip. Dominic, I would not sweep out from under anybody else's door, son. I'd sweep out from under my own door if I was you. That means mind your own business.
If he doesn't come in with the haircut, he was.
No, of course not. What do you think this is? College freshman year hazing? Anywho, Stephen's right. We got to come up with two equations. Well, we're staring, boys. We're staring right at them. Okay, first equation is x plus 300 times t equals 1080. And that's one equation in terms of two variables. The other equation is x and then t plus 1 equals 2400. Or excuse me, just 240. So I said this the other day. I hope you guys were listening. This is a nonlinear system. It doesn't look like the plain old ax plus by equals c. It's a nonlinear system. What did I recommend that you guys use to solve that system? Somebody said it. Stephen's paying daggum attention, that boy. Substitution. Okay? Now, substitution is just one of our three techniques. The other two were graphing and eliminating. The substitution is the way to play here. All right, so suppose that it's just be easy down here in the second one. Suppose I divide both sides by t plus 1 to get x by itself. Okay? You know, to be honest with you, that's not going to be a smart idea because I don't want to solve for t. What do I want to solve for? Let's solve for x. Let's do it the other. We're going to be smart students. We're not going to waste time. So let me come down here. What we'll do is we'll get t by itself. So t equals 1080 over x plus 300. And what we'll do is we'll plug that into the other equation. I don't need to tell you how substitution works. You guys have already gone through this. This ain't your first rodeo. Okay? So we got x, and then instead of t, it's that new fraction, 1080 over x plus 300 equals 240. And I would just do, what did I forget? What did I forget? Plus 1. You guys are awesome. Thank you. So plus 1 equals 240. Is that good? X and then t plus 1. Awesome. Hey, look, by the way, that goes to show you can know what you're doing. Like, I hope it's obvious that I know what I'm doing. But you can still make mistakes if you're rushing and you're just kind of flim-flam going through the motions. Okay? So pay attention to the details. Divide both sides by x, and we got ourselves a nice, neat little rational equation. We got 1080 over x plus 300 plus 1 equals 240 over x. I said that's a rational equation. Peter's about to tell us how we solve rational equations. Kill all the fractions by multiplying everything times the LCD. Camden, you had a question? Yeah, divided both sides by x. Divided both sides by x. All right. At this point, I should be able to lean on you guys to say, hey, we have now successfully set up our equation. We have finished steps 1, 2, and 3 of this 5-step process. Remember, step 1 is figure out what they're asking. I highlighted that. Step 2, assign a variable. We used the chart to help us organize those. Step 3, we made sense of the system of equations, boiled it down to one equation. And now step 4, we're going to solve that one equation. I'll zoom in a little bit right here. And if we solve this one equation by multiplying everything by the LCD, can we do that instead? I always ask two questions. What cancels out? And what's left over? So first of all, can we all agree that the LCD is not just X or not just X plus 300?
It's X on the X. Yeah.
It's X and X plus 300 because we want that each denominator to cancel out. So I got to put that on every fraction. That's my LCD. I got to multiply it here, here. I said every fraction. I meant every term of the left and every term of the right. Now, again, I don't want to take the time to write that up. So let's hit Cannon Haney up with a question. Cannon, what's going to cancel on that first fraction?
X plus 300.
X plus 300 is going to cancel on the first fraction, leaving me with 10, 80, and that X. Very good. Okay. Let's see here. Sebastian, what cancels out on the second term? Trick question. Nothing cancels on the second one.
Wait, why not?
Because there was no fraction. There was no fraction on that middle one. We just times it by 1. We times the LCD by the first fraction, and then we times the LCD by the second term. So nothing canceled out. Sorry for my trick question. Nah, let you now we are talking about that. So go ahead, Cam. What cancels? And what's left over? Fabulous. Okay. Now we've got what kind of equation, Cole?
It's quadratic.
Very good. It's a quadratic equation. I know Ethan Cannon heard that, so Ethan Cannon is going to tell us how many solutions said quadratic equation has.
2.
It has 2, just like every good little quadratic equation. This one's going to have 2. Let's do a little bit of distributing. I really should lean on you guys to do this for me. Well, we're going to divide by 10. X squared plus, oh, actually, we're not going to divide by 10. Never mind. Plus 300x, 240x plus, what's 240x, or 240 times 300?
72,000.
Yeah.
Woo, dog, yeah, that's a big number. 72,000. All right, let's get everything on one side. X squared. Subtract 240x from both sides. We get 60x. Put 60x with 1080x. What's that, 1140x? Are y'all seeing any of this as work that y'all got done last night?
Yeah, yeah. Can you like take a
I'm
second?
confused.
But it's a 60.
1140x.
Combine the whole entire left side first.
Oh, Cam, you could do that totally.
Okay?
Yes. Different strokes for different folks. So like in my brain, this is just me. In my brain, I thought, well, it'll be easier for me to go ahead and put these two 3-digit numbers together and then attack the 4-digit number. That's just how my brain was working. You could definitely say 1080 plus 300 is 1380, and 1380 minus 2400 or 240. So whatever floats your boat. But what do we got? Minus 72,000 equals 0. Now look, y'all are at the point where number one, every quadratic equation that you solve is factorable, because I have not taught you the quadratic formula yet, have I? Number two, that's a big fat number, okay? 72,000, I'm not gonna want to come up with all of the factor pairs of 72,000. That would be ridiculous. So I'm going to use a calculator or a computer to help me factor it out. There's nothing wrong with that at all on a homework problem where you're working like this. Because is this a question about how to teach you how to factor? No, we've done that, got the t-shirt, moved on, okay? This is a word problem where we're trying to figure out how to set things up and solve them. So I got no beef if you took this and you plugged it into, let's say, a Mathway or a Delta Math, not Delta Math, Simbo Lab or whatever online tool you wanted to use.
Oh, no, math.
So you wouldn't give us a question like this.
That is a correct statement. I would not give you one on the test like this or a quiz like this, where the numbers are so big that you're not going to want to factor it by hand. Has anybody got this factored out by chance? Hey, no shame. So x equals negative 1200, which probably has a likelihood of being a what? Extraneous solution, right? Because what is x? What does x stand for in this problem? All right, that's why I highlighted it. The speed of the car. There ain't no car going negative 1200 miles an hour. Okay? But 60 is very reasonable. So, okay, Ferris Bueller. Y'all seen that movie? Please tell me that reference is not lost on people.
Nope.
Okay, so can we all agree that 60 is a good number? Okay. Now, amongst yourselves, y'all are having a little too much chitty chat. What are some other questions that you might have on this assignment? 315.
Like everything past 315. I'm bad at making those things.
Okay, well, hey, look, that's what I taught you to do today. So no shame in that. Looky here. I got it highlighted in yellow. It says P varies directly as Q. All right. So up there at the top, right here, we're going to say P equals K times Q. That's just straight up translation from English. If I see P varies directly as Q, that's P equals KQ. If I see Eli varies directly as Sebastian, Eli equals K times Sebastian. It don't matter. Whatever that is, I know direct means multiply. All right, and then it gives me this initial condition. It gives me the P, it gives me the Q, so I can solve for what? I can solve for K, which we did down here. You know, there's the P, there's the Q. Divide both sides by the 3. We got K equals 3.2. And then the last one, this is actually a little bit easier. All they wanted to know was, okay, can you plug the K in and leave it in terms of P and Q? So we got P equals 3.2 times Q. That's all sure. Like the little bit further on, what they will do is they'll say, okay, hot shot, now that you know what K equals, can you tell me what would Q equal if P were such and such? And that's where you do your third step. You use K to extrapolate that final answer. Follow up. All right. Hold on, it's slowly getting there.
Even one day.
Did you take a nap yesterday?
I just slept in.
I think a lot of that.
Good.
I played some
What's up?
Minecraft.
Yeah, so I didn't.
Hush, 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 I can't hear.
I didn't put A equals to this. I put
If I got the number,
What's your question?
would that be good?
If I said, hey, what's the constant variation or constant proportionality, you told me that number, that'd be fine. I don't care what you call it. Typically, we use K conventionally, you know, but as long as you know what you're doing, that's fine. Number 20. Okay, number 20, I love this. Easy question once you figure out about variation. Pay attention here because it says the length of a spring stretches directly as the more weight you put on it. So imagine I got a spring attached up here, and we hang a light weight from it. It ain't going to stretch it very much. We hang a big weight from it, it's going to stretch a bunch. So write the equation that relates this. Okay, so we wrote L equals KW, where the more weight, the more length, okay? And then they gave me an initial condition. This initial condition, they said, all right, when you're hanging a 10-pound watermelon from the spring, it stretches it down 5 inches. So we said, all right, 10 pounds goes in for W, 5 goes in for L, and we solve for our constant. We solve for that factor that winds up being a half. And then we write up our equation, L equals 1/2 W. And then, we plug in that final bit. It says, how much watermelon would have to stretch the spring down to 6 inches? And so we plugged in L for 6, multiply both sides by 2, we got a watermelon that weighs 12 pounds. Okay? Pardon? A just wanted me to write the equation. So like, I guess A would be asking this, and then B would be asking that. Oh man, you're gonna, like Dominic said, you're gonna hope and pray for variation problems, because those are the ones that are pretty straightforward, pretty easy. All right. What can be more challenging is when we get those dirt problems or the work problems. Did you guys have any work rate problems on this one? Like Johnny can paint a room in 10 hours, his brother can paint it in 9. If they work together, how long does it take them? Were those pretty straightforward after you learned about that Wednesday?
Yeah.
No, class is almost over. Sebastian?
Give me any I can combine this and the, like, bullet sense.
Combine variation and dirt?
Yeah.
No, those two are pretty separate. Next one.
There's a 310, I was wondering if that is
All right, hold on. 310. 310. Work rate. I think I did this one last year, so I got my notes saved on it. But, okay, so it takes them 2.5 hours. Levi, can you see that, or do I need to zoom in? All right, so like I would work it out that way. They each spend an hour working on it. Levi completes 2/5 of the job. His dad, we don't know how much of the job he gets done. It's just 1 over X. And so in red, I wrote that equation up. 2/5 plus 1 over X equals the whole job, multiplied by the LCD of 5X. And then we got the resulting linear equation that we solved out for X. X equals 5/3 or an hour and 40 minutes. All right. Now, you guys at home, y'all be safe, healthy, and happy. Live Jesus in our hearts. Forever. All right, I'm going to cut you loose. Thanks for being here. And you guys that are here in person, we got about a minute till the bell rings. Y'all go ahead and pack it up, pack it in. I'm going to come around and spray the desk in just a second.